been a while, 12 days since the last time we had a class. So let me remind you what we were doing. Excuse me. Remind you what we were doing, and then also why we were doing it. So we're trying to do effective field theory. The actual thing we were doing, we were in the middle of a, the linear sigma model. And I have to wait for it to come up here. In the calculation, we had two different representations, and we calculated a scattering amplitude. So in the first representation, the one on the top there, this is the usual way of doing a linear sigma model. It has all these polynomial interactions, meaning there's no derivatives in the interactions. And we did the scattering amplitude where we did the exchange of the sigma tilde plus a contact interaction. And it was something like pi minus pi 0 goes to pi minus pi 0. And we got some number out which went like q squared over v squared. So it had a momentum dependence in it. But then we were able to reproduce that by just taking just the lowest order piece here, the d mu u piece, and writing just the contact interaction there, and you got the same thing. So you were able to reproduce it with just the light degrees of freedom, and you didn't need the heavy exchange. Okay, so the question is, what does that tell us? Well, one thing it tells us is it tells us that we don't need that heavy particle around. And in a way, that's what the why of what we're doing it is. So why are we doing it? Okay, so the goal here is to write a Lagrangian with only the light degrees of freedom. Okay, the heavy ones aren't active at low energies, and so there's really no reason why you need them. The technical phrase for this is going to be integrating out the heavy one. So whatever the heavy particle, you remove it from the theory. And the interesting thing is you're left over with the non-renormalizable Lagrangian. In this case, what we ended up with was v squared over 4 trace d mu u dagger. Okay, so that's okay. But then the real goal, the real interesting thing is that you can treat the effective Lagrangian, so this is some effective Lagrangian, as a full quantum field theory. Okay, you might have thought that we had to go back to the full theory, the original theory, to do quantum loops, because this one's non-renormalizable. And so the trick that we've learned how to do is this loop processes, how to do this in the effective theory. Okay, so that's what we explore today a good deal. Okay, any questions about where we were, what we're doing, the goals? Well, in this particular case, we can pick them out of the Lagrangian because we solved the theory. We found the ground state, and we know that the pions are massless and the S or sigma turtle is heavy. In other cases, like gravity, when we do this, for gravity, we'll just know it from experiment. We know that gravitons are light, and the rest of the theory, whatever it is going to be heavy because we don't see it yet. So in some ways, it's an experimental question. Okay, anything else? All right. So here's the correspondence. The full theory is so you integrate over ds, d pi, e to the I into d for x, L. The Lagrangian would have S, it would have pi in it, would be the full Lagrangian, so full. And then if you're looking to do interactions with the pion field, you'd add some source, and you differentiate with respect to those sources, gives you the various matrix elements that you want. And now we're going to integrate out this S. And we're going to write exactly the same thing as now. It's just an integral. You still have d pi. You have e to the I integral d for x, L effective, function of pi only, and then j dot pi. Okay. So the goal is to have these guys make the same matrix elements. Okay. And so this is an operational definition. You just do that path integral. There's a couple of things to point out here. So here this involves only pi. That's only the light degrees of freedom. But this part here, this integral d pi, means that this is still a full quantum field theory. Okay, this wouldn't make sense. It wouldn't make sense unless you still had that pi integration there, because you still have all those pion loops to do. But we were faced with the fact that this is now a non-renormalizable theory, this L effective. The other thing to say here is that L effective is local, because S is heavy. So it doesn't have any long distance propagation or anything like that. So those are tied together. Okay. Now we can actually do this at tree level. So let's do it at tree level. It's pretty easy. Okay, at tree level means you're just exchanging a heavy particle without any loops. Okay, so our Lagrangian, we have v squared over 4 trace d mu u dagger, and we had a coupling. It was v over 2s trace d mu u dagger. And then there was the S part, the 1/2 d mu s squared minus ms squared, s squared. Okay. So this interaction here is just like some effective vertex. Involves one S and then whatever these pions are up at the top. And we learned how to, last time I did that, I did this thing with tree level where I did the completing the square and getting the result out from completing the square. And so I'm just going to go back and write the answer out. So this, so you do the complete the square trick. And integrate S. You know, it was the type of thing that last time I wrote it is e to the I S operator S plus JS. And then I completed that square, or let's make that D. Completed that square, and then we ended up with something that went like J 1 over ms squared J. Okay, and the exact answer is if you just go back and plug into that formula, that the effective Lagrangian now looks like it's this v squared over 4 trace d mu u dagger. And then the next piece is v squared over 8 m s squared. This thing squared. Take that whole thing and just square it. Okay, and then there will be higher order terms that will be like Taylor expanding that the propagator. Okay. What does this guy give? Well, you can sort of see this one when we did the scattering matrix element gave me something like q squared over v squared. In fact, that's exactly what it gave me. This one here is also going to have a scattering matrix element, which it's going to have 4 powers of the momentum. When I expand the fields, all right, it's going to look like roughly q squared, dimensionally q squared, q to the 4th, v squared, ms squared. It's got the 1 over ms squared. Okay. So it's 2 higher powers in the energy expansion. And it actually equals the following. It reproduces. When we did this plus this was in the original theory, we expand that propagator and we get terms that go like q squared and q to the 4th, q to the 6th. You know, the q squared piece got matched up over there. The q to the 4th piece got matched by this guy. Okay, so we still are reconstructing stuff from the original theory. Okay. So at this stage, we've got a bunch of things. We've got an effective Lagrangian. We've got it ordered by the energy expansion. And we've matched on to the full calculation at tree level appropriately, so we're still good there. The only other thing I should point out, and I don't have much room to do this, is that it's actually not important for the effective field theory, but it is, well, maybe it is. But we can still see the original symmetry. And this was U goes to U to left U R dagger. So the symmetry is preserved. This is a bit of a lesson in spontaneous symmetry breaking, just because of the symmetry here. You often say symmetry breaking, but here's a theory where you've broken the symmetry, but you can still see it. So it's actually better referred to as symmetry hiding. It's a hidden symmetry in the spectrum, but the symmetry still exists. It's not that it disappears. Maybe. Okay. Any questions at this stage? If not, I'm going to go to loops. Okay, good. Loops. Left, yeah, so let's devote a little. Yeah, so U goes to an SU2 matrix on the left, U and an SU2 matrix on the right, and they're different SU2 matrices. Okay, and that was when we had our original theory. We had the same symmetry, and I had at that stage called it sigma. Sigma was sigma plus I tau dot pi, and we showed that had this double SU2 symmetry also, two separate SU2 symmetries, and we've got that still in the final theory. Okay, loops. Well, one of the things we've done already is we've actually renormalized the effective theory already. Okay, that's because I use this theory as an example when we were doing the background field method. So before we did background field method, where we expanded around some background field with some fluctuation, and we integrated over the fluctuation, and we did this two ways. We did a direct calculation where I just wrote it in terms of things and found the infinities. We also did the heat kernel. Okay, and what we found was that when we did the heat kernel, there was divergences that had a different character, so they had the following. So let's write a more general effective Lagrangian. Okay. So I'm going to want to preserve that symmetry, the same symmetry that we started with. And so I'll write the first piece is unchanged. Okay. And I'll give these guys some names, L1 and L2. L1 trace d mu and d mu u. Excuse me. So give that guy a coefficient and give this guy a coefficient. So there's another one I could write out. It's trace d mu u d nu u dagger trace d mu u d nu u dagger. Okay. So the first one, the indices are the same inside the trace. The second one is mu and nu repeated. Those are the only two independent ones that you can write out of this order. You try You might try doing something like putting inside the trace d mu, d nu, d mu, d nu, and then taking the trace, and there's just matrix identities that can be used to reduce this down to these two. It's, in SU3, you need a third term. In SU2, this is the matrix identities. Get rid of this. Okay. When we did this calculation, so I at that stage showed you the end results. It's equivalent to the following. You get infinities. The infinities look like these terms with 4 derivatives, and you renormalize with L1 is L1 renormalize is L1 bare plus it was 1 over 384 pi squared 1 over epsilon minus gamma plus 4 pi and the L2 renormalized L2 plus 1 over 192 pi squared 1 over epsilon, etc. Okay. So we knew that we could renormalize this already from our previous work, and the other thing that I can't avoid pointing out is that divergence is a local, so that looks like a term in a local Lagrangian, and it retains the symmetries. Okay. The retaining the symmetries part is part of the background field method. The fact that we started off that way, we had the symmetries built in at every step of the way. But that's not the whole calculation. Let's now do the finite parts of loops. Okay. And here I want to spend a reasonable amount of time on this argument that you're going to get the same finite parts of the loops. Okay. And I want to do it by going back to some of the example that we did. So remember when we did the original theory, we had this sigma twiddle exchange plus this contact interaction equaling the same effect as the contact interaction with L effective. Okay. Now, I'd like to then use that correspondence looking at loop diagrams. I'm going to pick a particular set and try to contrast doing the loops in the full theory. So this is full and the effective theory. Okay. So in the full theory, we do the following. Okay. Let me imagine I'm doing the same process, so that I do pi minus pi 0 scattering. There's that diagram. There's this diagram. There's that diagram. And there's a box diagram. So I sort of group these together. The matrix element for this would have an integral d4k, 2 pi to the 4th, I've actually got the answers written out here, so let me just copy what it is, because that's what I want to do. So there's minus 2I lambda. Okay, let's close this here. I'm gonna always have propagators of these light pions here. Okay, those occur in all the diagrams. So I'm going to call one of them 1 over k squared, and the other one is then 1 over k plus p minus plus p0 squared. So I've got p minus p0 k, and that's the residual momentum. Okay, and then over here I have minus 2I lambda. Okay, so what I've written out there is that first diagram. 2I lambda, that vertex, 2I lambda, this vertex, 2 propagators. Okay, the next diagram that is the one with the 1 exchange there. It's minus 2I lambda v squared I over k plus p minus squared minus ms squared. Okay, so this is one where I have 1 propagator on the one side and then the 2I lambda on the other side. If I can complete this, then the other one here is plus 2I lambda v quantity squared I over k plus p prime minus squared minus ms squared. Okay, p prime is the pi minus going out on the final side. Okay, so actually, if you look at that, I've got all 4 diagrams. I've got the 2 vertices on one side, 2 vertices on the other side. I end up with these 4 diagrams. Okay, in the effective theory, I've only got 1 diagram. Okay, the effective theory, I just have that vertex, and so I just write out this diagram. That's the only diagram I have to do, but I have a different vertex there. Okay, so here M effective is its integral d4k, 2 pi to the 4th. The propagators in the middle there are the same. It's 1 over k squared, 1 over k plus p minus plus p0 squared. But then the vertices are different. If I've got my factors right, it's p plus squared over v squared and I over k plus p plus prime squared over v squared. Okay, so at this stage, you're supposed to recall that at low momentum, that vertex, that combination there, went to this at low momentum. And that was the calculation we did at tree level. This guy went to that at low momentum. Okay, so the low momentum parts of both these integrals are exactly the same. the high momentum parts are different. In particular, the top one, the full theory, is a renormalizable theory. This other one is a non-renormalizable theory. So low momentum agree. High momentum disagree. Okay, so one of the things you know is that the divergence get out of this effective theory are spurious. They don't really belong. But that's okay because they're local again. And so they go into a shift of L1 and L2. Okay, so they just change the values of L1 and L2 by some amount. And so the goal then is to match the calculations. So what L1, L2 reproduce the result. Okay, so you have to basically correct for the fact that the high momentum stuff is wrong. Okay. Well, we can do that. The calculation actually in the effective theory is remarkably easy. That's a pretty simple diagram to calculate. The calculation in the full theory is not so easy. One time when I taught this, I started off trying to do this, having the students do the matching as a homework problem, and it didn't work. It was too tough of a problem. And let me just actually show you one reason why it's so bad. I don't know if you've played around with box diagrams, but one of the things there is this box diagram. We've got two massless particles, pi's and pi's there, and we've got heavy particles there. Okay, and the box diagram is a terribly complicated thing. So here's a paper that was written that's the compact expression for the one loop 4-point function, the box diagram. So basically they're doing the box diagram. And so there's the box diagram. And somewhere down here is the result when you have two massless and two not massless. But you can see calculating this thing is not easy. They're going through all the calculation, and it's all this compact formulas. So here's what the result looks like. There's all these functions here, R1, 3, X, are functions of the masses and momentum around that are in this problem. And here's the special case here. I want two masses equal to 0. So here's two masses equal to 0. Still, you've got all these functions around. It involves the dilogarithms. I don't know. Anyway, there's no useful approximation to that. Okay, it's a complete mess. And if you actually had tried to calculate from first principles, you end up writing a paper about it. Fortunately, it's been done, but it's not an easy thing to be done. So the box diagram in particular is terrible. The box is terrible. But it's not so terrible if once you have it, you can actually Taylor expand it at low momentum. Okay, so but even that was too much for a homework problem. But Gasser and Lightfielder have done it. So let me come down here and grab the answer. Here's the answer. Bring it up. The wrong thing. Sorry. begin. Okay, let's try that. Let's try selecting the page. No. All right, I'm having trouble copying. So let's just look at it down here, and then I'll come back. I'll paste it up there when I have more time. So here's the full theory. The full theory has, so T is what I was calling Q squared before. S is P plus P, or P minus plus P0 squared. And U is equal to P minus P0 prime squared. So you get the first piece that we had before. That was the Q squared over V squared piece that we had before. Now you get M sigma is MS is the heavy particle. We get terms that go like Q to the fourth. We also saw that one at tree level. So that one was already there at tree level. But we get finite corrections to that. And then we get these pieces with the logs, etc. Okay. When you do the effective theory, you get the renormalized coefficients, which I already told you what they were. So I've absorbed the divergences into that. You get some stuff left over. There's some stuff left over. And you get the logs, just like that match exactly the effective theory. So this is, or match the full theory. So this is the correspondence. I said the low momentum stuff is exactly the same. And so there's the low momentum. And in particular, I draw your attention to the fact that there's an imaginary part sitting right inside of this guy here. S is a positive quantity. Log of minus S is log S minus I pi. So there's an imaginary part there, and this imaginary part comes from having on-shell states. So, Cody and Sarah, I don't know if you've seen that part of it. That if you have an on-shell intermediate state, you pick up imaginary parts. On-shell state, yeah. Okay, that you get imaginary parts on scattering amplitudes. Have you seen that before? It's unitarity. Let me do the quickie derivation of this is S is 1 plus IT is the scattering amplitude in the T matrix. S dagger S is 1 plus IT minus T dagger plus sum over intermediate states T. So let's put initial intermediate final Fi. It basically is the imaginary parts of scattering amplitudes are given by the rescattering of physical intermediate states. This is really a quickie derivation of it, but the rescattering here gives you imaginary parts. Okay, it's the same correspondence, and so down here you can see this piece here, the log of minus S, gives me the only imaginary parts. T and U are actually negative in this particular process. But anyway, the reason for pointing this out is that on-shell states are clearly low energy. That's as low energy as you can get because it's the same energy as the original state. So the loop isn't adding anything really. They did not use the Denner result. Yeah, they maybe they didn't have. To be honest, if you were going through this thing and were doing it, you'd probably try to do the Taylor expansion before you completed the box integral, just because. So I actually don't know how they did it. It's sort of in one of their papers. I know there's a paper by Anish Manohar where he writes the whole thing out in his bloody glory detail, this linear sigma model. But that's useless because it has all these dilogarithms in it. So the full answer does live out there in the Manohar paper, but other than that, I don't know. It's amazing. When I assigned it as homework, I thought it was going to be easy, so I hadn't done it myself yet. Oh, did you? Did you? Did you really? Oh, good. So then you agree that this is a painful calculation. So, but anyway, what you do see is the structure of the amplitude is essentially the same. In particular, the logs are the same, and you can match exactly the result by choosing a particular values of L1 and L2. What you see here is you see the tree level one. That was already our tree level matching, and you just get finite corrections from the loops. So it is sensitive to those loops, to the heavy mass. There's that log of sigma. But otherwise, they're just small, modestly sized corrections to these. So this is the idea of matching. So actually, that's what I was trying to do up here. So what we did is we did matching to the full theory. But we've actually accomplished something more. So we've accomplished a few things. We've simplified further calculations. Okay, so this one, since we did it out in detail, it was painful to do that in detail. But let's imagine you wanted to do another process. In the full theory, you'd start with a full Lagrangian, and you'd start grinding the whole calculation once again. In the effective theory, you can just do the simpler calculation. You just do the simple bubble. So this matching holds for all reactions. You do it once and for all, and you're done. And you can then calculate in the effective theory. And that's easy. So we've the second thing we found is it's actually easier to use the non-renormalizable theory. Than it is to use the renormalizable one. And we've been able to do perfectly good calculations this way. Even more interesting, I think, is we've identified the non-local, the low energy physics. Okay, and I have to go back to that page now to do it. In some sense, what you see here is that the stuff with just the powers is not a uniquely low energy physics. There's the two coefficients here, and just there's leftover effects, but that's just a renormalization trick. I could have absorbed those into those coefficients. So those aren't uniquely low energy physics, but the stuff that came without any free parameters and matched between the effective theory and the full theory. So in some sense, the most interesting line of this is the last one, that is the real predictions of the effective theory. So we saw this mainly from the logs. Okay. And the point of this is that this cannot look like a local Lagrangian. Okay, you don't get the logs of derivatives. When we're doing a local Lagrangian, you have derivatives. Logs you can't do a local Lagrangian for. There's imaginary parts. The say we accomplished here is we now know what to look for prediction. The predictions are not the constants. Those are not part of the low energy theory. They come from the high energy theory, but the propagation at low energy is a prediction. And we could see that we reproduce that by going through this calculation here where we compare the two of them together. There's our accomplishments for this part of the calculation. Okay, any questions from that part? Okay. Next thing to do is to point out that we actually have what's called a power counting theorem. Where I'm having trouble with my pen's not writing anymore. Did anyone see anything happen? I'm looking at the blackboard. Sorry, I have to start right there. It looks like my tablet froze up again. Let's just see if it comes out of it. Actually, let's do the following. Actually, let's spend a moment to just see if I can get out using the. First thing to do is save. No? All right. All right, sorry for the darkness. Let's see. Let's get the blackboard there. All right, so basically what I have to do is I'm going to talk through the power counting. Can you see this? Can you see this okay?
Yeah.
Okay.
Yeah.
Okay. The thing that we saw, the important part to carry away here, when we did one loop, we ended up with all of our effects being of order energy to the fourth. So I was calling that Q squared there. Here's our Q to the fourth term that we saw there. But the STMU was also like that. And in some ways you could do this just from counting powers of Z. Remember, this vertex here was Q squared over Z squared. So the matrix on itself is dimensional. If we do a loop diagram like that, you get one of them here, one of them there, and so you get 1 over v to the fourth. Not doing any work. Then there's some loop integral that's a function of the external momentum. And the function of the external momentum, right? But when you do this dimensionally, if there's no other dimensional parameter around, so you use dimensional regularization. So you get 1 over v to the fourth times something that comes out as external momentum. So it comes out automatically either s squared over v to the fourth, t squared over v to the fourth, etc. So generically, energy to the fourth over v to the fourth, because it has to give you this dimensionless coupling constant. Okay. And you can sort of see that this is going to keep working. If I did 2 loops, So let's imagine doing two loops. I guess the easiest way is just to do one like that. You're going to get 1 over v squared v to the 6th, and it will then be energy to the 6th. So the power counting is implies 2 more powers of the energy. So the theorem is Weinberg's theorem. Says that when you're working at energy squared, so two derivatives, 2 powers of the energy, you need tree level. Okay, that first piece didn't get modified by the loops. We got the energy squared piece strictly from tree level. If energy is a 4th level, you need the 2 derivative Lagrangian at 1 loop plus the 4 derivative Lagrangian at tree level. Okay. And that's what we saw. We did that. We had the 2 derivative Lagrangian. We did a loop, and we had those L2, L1, and L2 coefficients that we matched. If you continue on, Weinberg's theorem tells you the result. That you would do L2 at 2 loops, L4 at 1 loop, and L6 derivative at tree level. So as you proceed, you get more and more accuracy because these are small numbers. This expansion is an expansion in small numbers. You rarely need more than 1 loop or 2 loops to do something in an effective field theory. It's actually, in some ways, it's even better than the renormalizable theory. All right. Any questions on that part? So we'll see that for gravity also. This is important for gravity. I guess I'm having technical difficulties. I'm going to do one more thing, and then so I want to do matching versus measuring. Okay, the theory that we did this linear sigma model. And we did the procedure is called matching, where we calculated both theories. In fact, even though an easier thing might have been just to go out and directly measure these parameters. So if you have an unknown theory, so if your full theory is unknown or if it's complicated, you can measure. Again, you have to devote one reaction to doing this. So the particular case that we had there, if you had taken the pi minus pi zero scattered, you have the two different kinematic invariants there that you could use to measure those two parameters. And then use them in other cases. So instead of doing this complicated calculation, you could have just gone out, if this was a real theory, and measured it. And that's in fact what we do at QCD. So this is actually, in QCD, what I described as Curl perturbation theory. And while QCD, in principle, you can calculate these, in practice, you measure them. And one of the things you find out is QCD is not equal to the linear sigma model. And this is actually told to you by the measurements in the linear sigma model. The L1 is much, much bigger than L2 because that was the piece that survived the tree level, and loops made a small change in that. In QCD, when you measured L1, it's basically very close to minus L2. So they have a different pattern. So these coefficients, this L1 and L2, tell you the properties of the underlying theory, and QCD has a particular pattern. And just for the sake of a future number, these are a few times 10 to the minus 3 in QCD. So they're dimensionless numbers, and they live at about 2 or 3 times 10 to the minus 3. Okay. Now, because of the technical difficulties, I'll stop there. So when we come back next time, we're going to do general relativity this way, writing it as an effective field. Okay, good. Okay.
I haven't checked the rumor though. Do you guys end up making an offer?
We can pay 2 offers. Okay.
Yeah, but what happened?
We can't make 2 offers.
Okay. Good luck, fingers crossed.
Yes. I don't know if the official paperwork has gone out yet, but
Was it a 2-position search initially?
No.
So we just got.
I take credit for the 2 positions because they said, oh, we're just pretty dangerous like John next year.
So,
Yeah.
I'll be watching the rumor to see how it plays out.